All right, so let's do a quick review. Newton's first law has to do with one object. This is like cat, which is a natural phenomenon. It's inertia. It's going to keep doing what it's doing, either staying at rest or just moving off with a constant velocity. Just you have to force the cat or inertia to do, anything other than what it's doing. Think about it. A more massive cat, a larger cat, probably be a little bit harder to start and stop. Something to consider. This is the one that Newton kind of ripped off or rebranded or whatever from Galileo. So that one, make sure you know also not a force. My goal in life is to trick you that it's a force. Alright, so Newton's second law, this is what we've been going over. Basically, acceleration, net force, directly proportional. Bigger the net force, bigger the acceleration. Mass, inversely proportional. More mass, less acceleration. That gives you this, which you can state as Newton's second law. That's your acceleration equals net force over mass. Again, we draw the free body diagram for this. So if you recall, free body diagram, think about it. Free body, not free bodies diagram. It's one object. Think the dot. And look, on this, your normal force and your weight balance out. So your accelerating force or your net force is force of tension. That means there's a string. So anyway, now let's get into, this one's going to be important for what we talk about in just a second. Newton's third law. Newton's third law deals with more than one object. So it's kind of like, as much as this finger is pressing on the wall is pressing on the finger, like the bug on the windshield. Got the windshield, it is green for some reason, and a bug. Well, the bug applies just as much force to the windshield as the windshield is applying to the bug. So now the reason why the bug goes splat is because the bug is very delicate and the windshield is not. And so, it's kind of like this. You're applying a certain amount of force by sitting in a chair. What if the chair all of a sudden became made of a water balloon? Or the, cushion on the chair. You probably break the water balloon, but you haven't changed the amount of force. It's kind of like that. Be careful. Sometimes a lot of times you'll have things like I could draw maybe a free body diagram of the finger or the hand, and that would just be free body diagram, one object, Newton's second law. Or I could analyze how the forces are interacting. But basically what this says, a simple way to put this, forces happen in pairs that are equal in magnitude and opposite, I'm going to abbreviate opposite, in direction. Don't say, I know you might have heard this is for every action there's an equal and opposite reaction. If you think about it, that's really not specific enough because this deals with forces. Okay, so now we're getting into this thing called an Atwood machine. It deals with second and third law. Now, don't just copy this and think that it's something you can write back on your notebook. This is something, I'm just giving you a basic idea of how this thing works. There's going to be a massive twist to it for like a game or something that you need to set up tomorrow. So keep that in mind and, just be thinking about all the different applications of this and what I could do. Okay, first of all, you've got mass 1 and mass 2. They're connected by a pulley on a table. This is an ideal system. That means there's no force of friction. And this F subscript air, that's air resistance. That'd be a good thing for me to ask to see if you were listening with sound. So that's air resistance. Also, the pulley is massless. That means this isn't a really big, heavy wheel. And the string is like fishing line, not like a rope. Think about it. If this were a big tug-of-war rope or a chain, it would get heavier as it went on. But, the mass would add up. But if it's like a tiny piece of fishing line, it's going to, be negligible. Also, mass 2, in this case, is bigger, much more massive than mass 1. So let's analyze this. Hopefully you can see that this system, these two things together, we're going to first kind of consider them as that, is accelerating. It's accelerating towards the floor. Now we're going to zoom back in and look at the objects. Accelerating towards the floor means, for this guy, pointing down, right? Mass 2 is falling. Since this is accelerating towards the floor, well, it's got to clear the table first. So this is accelerating that way. These are the same because the system is accelerating towards the floor. And so, like I said, this one has to clear the table before it can fall. And it eventually could, you know, if you let this were high enough, would just swing over there. So, system's accelerating towards the floor. Now let's zoom in on the two objects. First of all, let's look at mass 1. Now you do know it's got weight and it's got normal force and they balance each other out. We're not going to really consider those because we're really just interested in what's accelerating it. So that's any forces going this way with acceleration or in the opposite direction. Since this is friction, there's only really one thing moving this. You always want to look, ultimately, yes, I know it's this, mass 2, but let's look at what's actually touching the box, and that's this string. So this is the force of the string pulling on the box, which is the force of tension. So we've looked at that object, and let's come over to this one and draw a free body diagram. See how we're drawing two different free body diagrams for the two objects, but the objects make up the system? So we've got weight, of course. Oh, let me show you this. mg, that's kind of, you got two masses, so we got to be more specific than that. So we're going to put m2g. That means the weight of 2. All right, probably should draw that just a little bit longer because it is accelerating downwards, so that's like your big force. Okay, and then look up here. It's got the string attached to it, and that's going to be your force of tension. Now at this point, I want you to look at the force of tension. The force of tension, it's just one. This is a system. So it's kind of like if you took a string or take something in between your hands and like pull it, it's like it stays tense because you've got the same force of tension. It's kind of like the spring scales we did today in both directions. They're basically, you got one of them pulling on the string and then the other one pulling on the string, and they balance each other out. So as a system, if we look at this as like an internal thing, like the kind of guts of the system, these two forces of tension don't really matter. This is where I'm going to warn you not to look at these kind of problems on Google, because people will put this in and mathematically like cancel out force of tension. It's a big old pain in the butt. You don't need to do that. Just look at it like look at it like a system, and you know that these can go away. And I'll show you a trick on that.